efficiently. But still, this is a lot of calculation per byte or per bit coded, so this is slower than binary codes, and noticeably so. One of the improvements you get from this, though, is that you're not working with code strings anymore, with individual characters that have a certain number of times it occurs. All you really need to do this kind of coding is how probable it is that each of those characters happens in your text file or whatever. And unlike Huffman coding, where you have to regenerate a tree every time the count of characters changes, you can change this distribution of what is how probable quite easily, which is called adaptive arithmetic coding. And you can even go a bit further and use different models, different sets of what is how probable based on the context, which again I'll define more precisely in part 2. But the basic idea is, for example, when you have an English text again, the character U is very probable if the last character you've seen before is a Q, because in English text you always have QU. There's basically no other letter that can appear after a Q in normal English text. So if the last character you've seen is a Q, you can use a different mapping of probabilities because the U is very, very highly probable. And with that kind of stuff, you can get a lot of compression improvement by using context. Again, trying to put more information, more knowledge about what has happened in the data before into your coding process. Anyway, this is already quite a lot for the first half or first part of the seminar. So do you have any questions so far? Nothing? I can't believe every one of you has no questions. Yeah?
I was just wondering, when you were comparing the Park 8 sizes of your two sound file, did the sizes include the algorithm to expand it again, or was it only the compressed data?
No, that was just the compressed data. The DPEG has about 300 bytes. But again, it's usually in the executable packer you use, so this is not really a cost you see, because it's always there anyway. Yeah. Any other questions? Yeah?
So which compression algorithm do you use for finally after the data coding and reordering?
I'll come to that in part 2, at the very beginning. Okay. No more questions? Okay, then we'll do a short 10-minute break or so, whatever you prefer here. And then we'll go on with part 2. Yeah, welcome back. Now for part 2. Again, small outline. This is a bit less. I don't actually think I'll end up at the whole 1.5 hours, but I wanted to have some time for more questions and answers, hoping that this time there actually are any. Yeah. The first one, which is called Dictionary Schemes and Context Models, if that doesn't mean anything to you, we'll see it later one. A bit of theory still. I'll try to keep this short because it's not really that important that you understand the details. And then we'll get into this section, which is just 2 subtopics, but both are, I'll talk about both extensively because this is how to reorder data and how to make it compress better. And this is, I think, what most of you are interested in. And I'll need the background from the section 4 for that. Okay, so on to section 4. And more specifically, so-called dictionary methods. In most types of data, you have lots of repetitions, which are usually a really high count of small 2 or 3 byte sequences that get repeated. But there are also a few really, really long ones, like when you basically Like when you would copy a whole subroutine from your program somewhere else, you would get a very long sequence that is exactly the same. Stuff like that. And how can we make use of that to make it compress better is the main question. And yeah, the idea is that you don't code each character individually, like you would in our previous section, but instead try to code whole strings with a dictionary, which is not the normal hardcover kind. You don't have a book of English words used for that, but rather you build a dictionary from the data you've seen so far, from the compressed data. That's the idea, because again, this ensures that your dictionary actually matches the data. If not the current data, at least the past data. And if the current input is found in the dictionary, like the 5 characters that are coming up right now, for example, you don't store those 5 characters individually, but a reference to the dictionary where those 5 characters are. And this reference is usually smaller than the string itself, because that's the whole point. You try to make those references small, so this kind of encoding pays off. Yeah, there can be either explicit or implicit dictionaries. An explicit dictionary is an algorithm that really has a dictionary, a table of strings, and maintains this explicitly. An implicit algorithm is anything that doesn't do this and generates this from the data somehow. A dictionary is not stored along with the data. This is not something you put in the header or similarly, like you would, for example, with vector quantization. Not a table you store anywhere, but a set. It's being built from the data. And this is not something you do in a pre-processing step, but this happens as you are compressing it. And it's built on the fly. Explicit dictionary methods are basically quite dead, because implicit coding is easier to combine with other algorithms for various reasons. And all good compression methods that you will see nowadays don't have a single algorithm they use, but try to combine different techniques, because each technique has its strengths and weaknesses, and when you combine several of them, you are usually able to get a good mix that allows you to get really, really good compression for a wide range of data types. But for completeness on explicit dictionary methods, for example, LZW, Lempel-Zip-Welch, is an explicit dictionary scheme, which is used in, for example, Unix compress tool, which no one uses anymore, the CompuServe GIF file format, and the modem V34 protocol, and so on. This used to be patented, which was a lot of trouble in the last few years with, for example, GIF files you had on web pages. The patent is now expired, but yeah, this patent basically nails shut the coffin of explicit dictionary schemes, because they didn't have the pack rate you would get with other techniques, and now with the patent trouble, no one used them anymore, so they're basically, not popular anymore. So, implicit dictionary methods. The most popular and most well-known of that is the so-called LZ77 scheme, and variants of it, which is done by Adrian Lempel and Jakob Ziff in 1977. This is really probably one of the most important publications in the data compression world, because this algorithm is the basis for, basically most packers you've used in your life. There are things like APAC, which is a DOS4K packer, or also bigger files for the packer used in UPX, or combined with Huffman coding, you get basically all popular packers like LHA, which is again pretty much outdated in ARJ, but also zip, RAR, CAP, and so on. Or if you combine it with arithmetic coding, you get LZMA, which is used in 7-zip and several current executable compressors, or Crunchy, which is a different variant of coding but also uses LZ77 combined with arithmetic coding, and lots more. This is really, really popular, and everyone of you in this room probably has used a variant of this in some way or other. What it does, it uses a so-called sliding window of fixed size.